Alright, silly people, here's the situation. Griffiths is going to have us construct a couple of linear transformation matrices by hand, just from a description of the transformation. Um, and then we're going to check it against the theory a little bit. So the first transformation that he wants us to do is a rotation of angle theta around the z-axis. So if you're looking down the z-axis or the k hat unit vector, this is what you're seeing. You see the I hat unit vector pointing in the positive x direction, and also a j hat unit vector pointing in the positive y direction here. And then whenever you rotate it, the new I hat unit vector, I hat prime, will just be an angle theta from where it used to be. And then the new j hat vector, j hat prime over here, also just an angle theta from the j hat direction, right? So just looking at this now, if we wanted to project I hat onto the ij basis, then we know that this x distance is just the cosine of angle theta, presuming that the length of the vector is still 1. And also this is just the sine of angle theta. So we know that I hat prime is equal to cosine theta I hat plus sine theta j hat. Similarly, if we were to project the j hat vector onto the basis of I hat and j hat, we know this distance is minus cosine theta, and this distance is actually, or no, that's not minus cosine theta, it's minus sine theta, yeah, because it's opposite, and then this is cosine theta for sure. So that means that j hat prime is just minus sine theta I hat plus cosine theta j hat. And since we're looking down on the z-axis while we're doing this rotation, the z-axis isn't going to change. Right. So the formula for linear transformations is that the new vectors, the primed vectors, will be the matrix that we're going to use times the original basis vector. So we know that I hat prime is going to be R, that's what I'm going to call the matrix, times I hat, and then j hat prime is equal to R j hat, and then k hat prime is equal to R k hat. So we can write this out in a better way. Let's start with the k hat equation actually. So we know that k hat prime is just equal to k hat, so it's just going to be 0, 0, 1. I'm going to write it in column matrix notation. And then the rotation vector, or matrix, we don't know what any of these values are yet, so I'm just going to call them a bunch of letters. G, H, J, just because I can. And then that is times the original k hat vector, which is 0, 0, 1. If you carry out that matrix multiplication on the right hand side, you just get C, F, J, and we know that that has to end up being equal to 0, 0, 1. So you can just kind of go component by component. E will be 0, F will be 0, and J will be 1. So we've already taken care of 3 letters of our matrix. So the next equation that we'll look at is the I hat equals R times I hat guy. So that's going to be cosine theta sine theta 0 for I hat prime is equal to our rotation matrix, which is now just A, D, G, B, E, H, 0, 0, 1 times the original I hat vector, which is 1, 0, 0. Carry out that matrix multiplication and you get ADG for the resultant column vector. We know that that has to equal cosine theta sine theta 0. So just comparing it component by component, we see that A is equal to cosine theta, D equals sine theta, and G equals 0. To take care of the last three missing elements, we need the J hat prime equation, which is looking like minus sine theta cosine theta 0 equals the rotation matrix times the J hat. So rotation matrix now looks like cosine theta sine theta 0 BEH 001 times 010, the J hat vector. So again, just doing the matrix multiplication on the right hand side, you get BEH for the resultant column vector. So you see that B equals minus sine theta, E equals cosine theta, and then H equals 0. Yeah. Which means we can write out the rotation matrix like cosine theta minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1 for rotations around z hat direction. Now, we're going to develop an intuition about this so that we don't have to do this every single time we want to construct a new basis from a linear transformation. So I'm going to copy these lines down, which we obtained from observing the rotation itself. And then notice that, okay, going element by element, cosine theta, minus sine theta, minus sine theta, sine theta, cosine theta, 1. What you're supposed to notice is that if you just go down a column of the rotation matrix, you get something that is identical to the transformed basis vector if you just treat it as a column vector, right? So that's the column vector that is I hat, that's the column vector that is the J hat prime, that's the column vector that's the K hat prime. We can develop an intuition about that for sure, and then use it to do the next couple linear transformations. The next one is going to be a little bit more strange. So now you're looking down the vector 1, 1, 1, pointing towards the origin. So you are going to see the I hat basis vector sort of pointing this way, the J hat basis vector sort of pointing this way, and then the K hat vector pointing this way. And these are all supposed to be like equally spaced, if you can't tell, because I'm bad at drawing. But then you're looking down this vector, and then you see that you're rotating 120 degrees counterclockwise. So I hat is going to be rotated 120 degrees. This is going to go 120 degrees. And this is going to go 120 degrees. So we're pretty much just replacing basis vectors with other basis vectors. So I hat prime is going to be J hat. J hat prime is going to be K hat. And K hat prime is going to be I hat. Yeah. Nothing too crazy there, I don't think. So with those in mind, we can write this new transformation matrix, which I'm just going to label A for rotating around 120 degrees. I hat equals J hat, so it's going to be 0, 1, 0. J hat prime equals K hat, so it looks like 0, 0, 1. K hat prime equals I hat, so it looks like 1, 0, 0. And that's awesome. And then finally, the last rotation, I'm not even going to draw a diagram for it because Griffiths describes it as just being a reflection over the xy plane. So nothing is going to change except for the K hat direction. It is now going to be just reflected across the xy plane, so it's minus k hat rather than just k hat. But then I hat prime equals I hat, and j hat prime equals j hat. So then this transformation, which I'm going to call B for reflection, is going to be 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Cool. We have to now check that all of these are orthogonal matrices. Orthogonal matrices being ones where the transpose is equal to its inverse, or more eloquently, what we're going to use, that if you multiply the matrix by its transpose, you get the identity matrix, right? So that means that to check our transpose, we need to go back to our rotation matrix, which is cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1, and then multiply it by the transpose. So cosine theta minus sine theta, 0, sine theta cosine theta, 0, 0, 0, 1 will be, yeah, that'll be the transpose. So just multiplying these together, cosine theta times cosine theta makes cosine squared theta, minus sine theta times minus sine theta makes sine squared theta, 0 times 0, and then this guy, sine theta times cosine theta makes sine theta cosine theta, cosine theta times minus sine theta makes minus sine theta cosine theta, and then 0, and then zeros here, and then this is going to be minus sine theta, or no, this is going to be cosine theta times sine theta, cosine theta, and then minus sine theta times cosine theta, so minus sine theta cosine theta, and then 0, and then this is going to be just sine squared theta plus cosine squared theta, and then this is 0, and so are these, and this is 1. Cool. So cosine squared plus sine squared makes 1. This will cancel out this. This is 0. This is 0. This will cancel out this. This is 0. Again, sine squared plus cosine squared is 1. This is 0. 0, 0, 1. So it is the identity matrix. So yeah, the rotation matrix is orthogonal. Then we have to check that our A is going to be actually orthogonal. And then I already forgot what that looks like. 0, 0, 1, 1, 0, 0, 0, 1, 0. Cool. That's A. And then we're going to multiply it by transpose, actually. So we're going to do A times A transpose. It looks like 0, 0, 1, 1, 0, 0, 0, 1, 0. Multiplying these guys. Yeah, that's 1. This is going to be 0, 0 here. You have just 1 here, no. It's 0 here, 1 here, 0 there, 0, 0, 1. Yeah, they are orthogonal, and then finally the matrix B, which we found, which ended up being 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Multiply that with the transpose, so 1, 0, 0, 0, 1, 0, 0, 0, minus 1. It's a pretty easy matrix transformation. It's just 0, 0, 0, 0, 1, 0, 0, 0, 1. So yeah, all these are orthogonal. The last thing to check is that the determinants are equal to positive or negative 1. So the determinant of the rotation matrix is cosine theta, sine theta, 0 minus sine theta, cosine theta, 0, 0, 0, 1. The determinant of that is cosine squared theta, 0, 0, plus sine squared theta, and then 0. Okay, so it's 1. Fantastic. The determinant of the matrix A looks like the determinant of 0, 1, 0, 0, 0, 1, 1, 0, 0. So it's 0, 0, 1. And then, yeah, it's just 1. Beautiful. Finally, the determinant of the matrix B is not going to be 1. Spoiler. But it's actually 1 times 1 times minus 1 equals minus 1, and 0, and 0, and 0, 0. So it's minus 1. And that's cool. That still makes it an orthonormal transformation. All right.